This is the continuation of last class video. So observe here, the next application is pulses swell when soaked in water. Means ಏನಾದರೂ ಕಾಳುವಿನ water ನೆನೆಸಿದಾಗ ಏನಾಗುತ್ತೆ, swell ಆಗುತ್ತೆ, ದೊಡ್ಡದಾಗುತ್ತೆ. That is the best example for osmosis. And water rises in the roots and water rises in the roots and stem of plants. So you know, when we are pouring water to the plant gets start to absorb the water. That water passes to the from roots to stem in the plant. That is only by osmosis. Okay, all these things are happened by the process of osmosis. Now here the scientist Van is observed in the year of 1887. After knowing the examples of osmosis, the scientist Van observed in the year of 1887 the dilute solutions is obey the law of ideal gas equation, and also it obey the ideal gas. Therefore for osmotic pressure for dilute solutions is given by, we know that ideal gas equation PV is equal to nRT. This is the ideal gas equation, and all dilute solutions obey the law of ideal gas equation and ideal gas. In the year of 1887, the scientist Van observed. Therefore, here P is nothing but what? Pressure of the solution. Pressure of the gas. In the case of ideal gas, P is the pressure of an ideal gas. Therefore, for osmotic pressure, we are representing the pressure is pi. Okay, pi V is equal to nRT for dilute solutions. Okay, are you understanding? This is for dilute solutions. Pi V is equal to nRT, where pi is nothing but osmotic pressure and V is the volume of the solution, N is the number of moles, and R is the universal gas constant, and T is the temperature. Therefore, pi is equal to, from this equation, pi is equal to osmotic pressure, pi is equal to N divided by V into RT. Here N by V is equal to what? N by V is equal to concentration of the solution. Therefore, pi is equal to CRT. Where C is nothing but concentration of the solution. And if N is equal to number of moles, that is weight divided by molecular weight of a solute. So you know, solute is represented as 2, or we are taken as a component B, right? Therefore solute, that is weight divided by molecular weight, W divided by M. So here take B for solute, or take 2, you are sure. This is the N value, that is weight divided by molecular weight. It means number of moles of solute. Therefore substitute in the equation this one. Pi is equal to N is nothing but what? WB divided by MB into, this is the place of N, and RT divided by V. This is the final equation to determine molecular mass of a solute. MB ಅನ್ನು determine ಮಾಡಬೇಕಾದ್ರೆ ಈ equation ಅನ್ನು ಯೂಸ್ ಮಾಡ್ಕೊಂತೀವಿ. When they are given osmotic pressure and weight of a solute, universal gas constant, and the temperature volume. All these terminologies are they given and asked to calculate molecular mass of a solute. This is the relation. Or if they given all these values and asked to calculate osmotic pressure, this is the equation used to calculate osmotic pressure and molecular mass of a solute. Okay, this is given by the scientist Van in the year of 1887 by comparing ideal gases equation to the dilute solutions. The next concept is isotonic solution. Isotonic solution. You know, iso means same. Then isotonic solution is defined as the solution which having same osmotic pressure is called isotonic solution. The solution having the solutions having same osmotic pressure is called isotonic solution. If we are taking two solutions, for those two solutions the osmotic pressure will be same, then we call both are isotonic solution. That is, the solutions having same osmotic pressure is called isotonic solution. This is only by having equimolar masses of these solutions. Means two solutions having same equimolar masses, then we are said to be isotonic solutions. Okay. Then next one, hypertonic solution. Hypertonic solution. So you know, hyper means high, hypo means low. So hypertonic solution is defined as the solution which having higher osmotic pressure than the given solution is called hypertonic solution. That is, the solution has higher osmotic pressure than given solution. Such solutions we call what? Hypertonic solution. Then next one, hypotonic solution. So here we are learning different types of solution based on osmotic pressure. Okay. Now take third one, hypotonic solution. So defined by the same like definition. That is, hypotonic solution is defined as the solution has lesser osmotic pressure than the given solution is called what? Hypotonic solution. That is, the solution has lesser or low osmotic pressure than given solution. Given solution is called hypotonic solution. This is the different types of solution based on osmotic pressure. Now, after knowing these, take reverse osmosis. The next concept is reverse osmosis. Already you know what is meant by osmosis and the examples, then the mathematical equation, and you know the osmosis is an best example for colligative property, and the mathematical equation that is given by Martovs, and also you know the dilute solutions is obey the ideal gas equation. Okay. Now we are going to learn reverse osmosis. This reverse osmosis exactly opposite of osmosis, so that we call reverse osmosis. The word itself says. So here observe, by the principle of reverse osmosis only, the purification of waters is working. Means water purifiers are working on the basis of reverse osmosis, and also the sea waters, marine waters are purified by the principle of reverse osmosis only. Okay. So here observe, you know, osmosis is nothing but osmosis. First we are revise the definition of osmosis. That is, osmosis is nothing but the flow of solute particles, the flow of solute or solvent. So observe the flow of not solute, flow of solvent particles from solvent to the solution. Flow of solvent particles from solvent to the solution is called what? Osmosis. So observe, when we are putting here pressure, external pressure, the solvent particles will be moves from solution through semipermeable membrane, or the moment of solvent particles from low concentration to high concentration is also called as osmosis. Okay. Similarly, in the reverse osmosis, it is exactly opposite. When we are applying the pressure which is excess to the osmotic pressure, then the particles, that is solvent particle which is present in the solution, will be moved to the solution, that is called reverse osmosis. ನಾವೇನಾದರೂ ಈ ಎಕ್ಸ್ಟ್ರಾ ಪ್ರೆಷರ್ ಅನ್ನು ಅಪ್ಲೈ ಮಾಡಿದ್ರೆ ಆ ಪ್ರೆಷರ್ ಅನ್ನೋದು ಆಸ್ಮಾಟಿಕ್ ಪ್ರೆಷರ್ಗಿಂತ ಜಾಸ್ತಿ ಇದ್ದಾಗ ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ ನಾವು ಇಲ್ಲಿ ಪ್ರೆಷರ್ ಅನ್ನು ಅಪ್ಲೈ ಮಾಡ್ತಾ ಇದ್ದಾಗ ಸೊಲ್ಯೂಷನ್ ಅಲ್ಲಿರುವಂತ ಸಾಲ್ವೆಂಟ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಸೊಲ್ಯೂಷನ್ ಇಂದ ಸಾಲ್ವೆಂಟ್ ಗೆ ಸೆಮಿ ಪರ್ಮಿಬಲ್ ಮೆಂಬ್ರೇನ್ ಮುಖಾಂತರ ಏನಾಗುತ್ತೆ ಪಾಸ್ ಆಗುತ್ತೆ. That is called reverse osmosis. Okay, based on this only we are purifying the water. Or water purifier plants are working on the basis of reverse osmosis only. Okay, when we are applying extra pressure, that is excess to the osmotic pressure, means higher to the osmotic pressure, then the solvent particle is moves from solution to the solvent, is called reverse osmosis. So take definition. The definition is the extra pressure or the higher pressure which is, or the pressure which is higher to the osmotic pressure, is applied on solution, then solvent particles will move from solution to solvent is called reverse osmosis. Okay, that is called reverse osmosis. So ನೀವು ನೋಡಿರಬಹುದು ವಾಟರ್ ಪ್ಯೂರಿಫೈಯರ್ ಪ್ಲಾಂಟ್ಸ್ ಮೇಲೆ ಹಾರ್ಗೋ ಅಂತ ಬರೆದಿರ್ತಾರೆ. ಹಾರ್ಗೋ is nothing but what? Reverse osmosis. This is the definition of reverse osmosis. Okay, so after knowing reverse osmosis, we are learning one top factor.